now it is? Very good. Okay, last time we started talking about numerical algorithms. That seems loud to me, is that okay? Is that right? Okay. Numerical algorithms for exploiting the properties of Lyapunov functions, trying to find Lyapunov functions or find Lyapunov certificates for some nonlinear system. And we talked about a couple big ideas, right? So I would say last time, so two ideas that we're going to build on immediately here. One was the clever parameterization. So when we were working with function approximators to think about cost-to-go functions, we talked about the linear function approximators. Which can take positive and negative values. These are some basis vectors, nonlinear vectors of phi. And one of the big ideas that we did yesterday, or Tuesday rather, was that for Lyapunov functions, since we'd like Lyapunov functions to be positive definite sort of by construction, let's choose a parameterization that helps us with that, and take the same kind of basis functions, but put them into some form like this. And add the constraint that P is a positive definite matrix. Okay, so the rule of alpha here, my coefficients, my parameters that I'm searching for here times some functions that are given to me, is played by P here, right? But it's basically the same thing. All my parameters are in the matrix P, and I have an additional constraint on those parameters that the matrix is a positive definite matrix, okay? And we talked about how that can be surprisingly, interestingly, formulated with convex optimization. Okay, so is this a linear function approximator? Is it a linear function approximator? It's a quadratic form, but it's still linear in the parameters phi, or alpha, sorry, p alpha. I could take the trace or I could rewrite this in this form perfectly. So it actually is still a linear function approximator, because what matters is not the linearity in x. Neither of them have linearity in x. What matters is the parameters up here only linearly. Okay, it's hidden by being inside there, but it's still, every term, if I were to multiply this out, just has one sort of coefficient from this. It's linear. And do you understand that this can only produce positive numbers or zero? And I mean, if I just write it y equals phi of x, then this is the definition of a positive definite matrix, is that these are always greater than zero, right? So it doesn't matter that it's through some transformation, as long as you get the same number on both sides, then this is always greater than zero. Okay, so we can still search over this kind of class of functions with convex optimization by adding this convex constraint, semi-definite or positive definite, but we use semi-definite programming to enforce this constraint. Okay, this is I complained a little bit at the end. Sorry about that, but it is still a convex optimization, but it's a little bit more finicky of a convex optimization. Solvers tend to complain at you a little bit more, and you can't solve quite as big problems. So if possible, avoid that type of constraint, but it's super useful and we're going to use it today. Okay, that was the first idea. The big sort of trick was that we can, by construction, well, almost by construction, but we can write this parameterization so that we can search over positive functions. But that only talks about v. We also want v dot to have some positivity, or negativity actually, conditions. And so the second idea was this idea that by sort of function matching, by coefficient matching, you can actually write more complicated. You can use this trick again to put a constraint on v dot in certain cases. And I think that was most easy to see in the linear Lyapunov function case. We talked about, well, in that case, all that matters really is the optimization we wrote. If I know how to write optimizations that accept positive semi-definite constraints. Let me write it like this since I'm saying positive semi-definite. If I have a tool for optimization that accepts constraints like this, and a tool that can accept linear constraints, which semi-definite programming can do, okay, then I can also, that means I can also write constraints like these are the linear matrix inequalities. Right? Again, this is linear in the coefficients p if I'm searching over p, and alpha is, and a is given, right? And the reason that somehow a solver that consumes optimizations like this can solve problems like this is because we could always introduce an additional set of decision variables, ask that to be greater than or equal to 0, and then say a linear set of constraints which says if I go through the elements of P2, they have to line up to be A times the elements of P, right? That's a whole line of linear constraints. And since this and this are both in there, that means if I can do this, then I can also do problems like this. Okay, so that's what we're going to do again to make v dot work in the nonlinear case, is we're going to say I'm going to write a second function that looks like this, okay, also positive definite, and then I'm going to try to make the equations match, the same way we did here with a bunch of linear constraints. It turns out you can't always do that, but one place we get really far, both with our theory and our numerical algorithms for doing that, is with polynomials, okay? So idea for today now is optimizing over polynomials. Positive polynomials. So if I have some polynomial equation, which again is going to have coefficients, which is linear in its coefficients, alpha 0, alpha 1 plus x, alpha 2 times y, alpha 3 x squared, let's say. I mean, I can go on and on, but I do want it to have a finite number of coefficients. At some point, it'll stop at the d power, okay? If I have some finite degree polynomial like this, then I can guarantee that p of xy is greater than 0 for all xy if I can find something like that, right? Now let's think about what happens here. I called it m instead of phi because m in the polynomial case is just a vector of monomials. So no sums, just x, y, xy squared, stuff like that, right? Just one of each of these terms. P represents the coefficients, okay? And the amazing thing is that, or the nice thing about polynomials is that I can take two polynomials, ask if they're the same, by just matching the coefficients on the different polynomials. Right? So if I collect all the terms that are multiplied by x, if the coefficient of that matches the coefficient of this, and I go through the list, and that's true for all of the monomials, then I've got equality. Okay? That's one of the important properties of polynomials that make this work. That's not true in general, right? If this was sines and cosines and other things, then I might have an arbitrary list of trig identities to check in order to make that equality hold. That's not impossible, but that's more work, okay? All right, so for example, quick quiz. For all x, real x. Yeah? How do you know that's always greater than 0? Right, this is clearly by itself always greater than 0 because x is squared. This is always greater than 0. Okay? What about, I picked a nice example here, 2 minus 4x plus 5x squared greater than 0 for all real x. That one's a little harder to see, right? It's got some positiveness, but you don't know if that negative 4 is killing you or not. Okay, but I'm going to convince you that it's positive by saying 2 minus 4x plus 5x squared equals 1x I'm going to put it into a quadratic form. Now, this term, when I multiply through, is going to be the only term that has no x's in it, so it better be 2, right? This term, let me do it in 2 steps here. This is P11, P12. It's going to be a symmetric matrix, right? Okay, so P11 we know has to equal 2. P12 is going to contribute an x term, as is this one. So we actually get 2 times P12 has got to equal negative 4. Again, what's important is that these are linear constraints. Matching the coefficients are linear constraints that we're going to add, right? And then P22 is going to be 5. So that gives me a matrix 2, negative 2, negative 2, 5. And if you take the eigenvalues of that, it's 1 and 6. So. Okay, so because of, this, positive definite matrix, the definition of the positive definite matrices here, I've shown you that this equation can be rewritten in a quadratic form with a positive definite matrix. Therefore, it must always be positive. You could also factor it a different way and convince yourself easily, okay? But that's the idea we're going to use today, putting it in a quadratic form. Okay, so in the same way that taking the semi-definite programming language and making this observation, we sort of level up. We get a whole richer class of optimization problems we can think about. We can write our solver interface. We can write our code that just accepts constraints that look like this, and behind the scenes it'll do this trick if it needs to hand it to the solver. Okay? Somehow our representation language got more powerful. Okay? Now with this trick right here, once again, our representational power just got more, we just leveled up, right? And we can write optimizations. We can say minimize some, let's say, minimize alpha C transpose alpha, we can minimize linear objectives with linear constraints, or SDP constraints, but it's a little weird to write a alpha less than or equal to b, but hope that's what we'll do here just to make it clear. And we can say subject to p of x with the coefficients alpha greater than or equal to 0, but I want to be a little careful here. I showed that this, if we can find this equation matching, then that guarantees this. But I haven't actually showed the counter implication. So what I'm going to write instead of this is I'm going to say is a sum of squares. Okay, so being able to find a decomposition of a polynomial, this is a decomposition of the sums of squares decomposition. That's sufficient to prove that the polynomial is always positive. It is not a necessary condition in general. Yes?
What is C in this case?
C is the cost function, so you're allowed to have any linear objective. So, yeah. These are just constant cost terms. It's like my Q and R matrix in LQR.
Excuse me.
Yes?
Do you need to define that P should be positive semi-definite?
Yes? I did maybe not write it this time.
Is that a part of the SOS decomposition criteria?
Right. So what we've now, in our leveled up world, we get to tell the solver, some solvers consume this as a front end where you can just say, here's a polynomial, make it sums of squares. Behind the scenes, just like the LMI, it'll construct a new set of decision variables, put a constraint that they're positive semi-definite, and then it'll add a bunch of linear constraints in order to make that work, and solves a semi-definite program behind the scenes. So this is just a front end, a shiny user package that we put on top of a semi-definite programming solver. Okay? So what are the decision variables in this problem? What are the decision variables? Alpha. Is X a decision variable? No, right? This is saying, I'd like it to hold for all X. Decision variables, you find a single value, right? X's are called the indeterminants. You should read that as, I want this to hold for all X. I don't know what X is, it's indeterminate, but no matter what X is, I'd like this to be positive, okay? So there are now two types of variables flying around in our sums of squares optimization, the decision variables and the indeterminants. Yes?
So does the solver actually make it hold for all X, or just make it hold for a large bunch of sample points?
That's for all X, right? That's exactly the same way that a quadratic form, it's the positive definite matrix for X transpose PX. That means that's positive for all X, right? And for this, in the same way, this is really a certificate if I found a P for all X, no samples involved. That's the big idea. I want that to land. Yeah.
Not actually, I see. So it's just a constraint. So SOS just means that it can be written in this form of some vector P's vector transpose, where the vectors are monomial entries and the P's positive definite.
I agree with everything you just said, which was that sums of squares means you can write it in this form. The only word, I don't like the just, because it's amazing. This means that, that you can do things that you shouldn't be able to do with convex optimization. Okay, let me give you, I will go a little bit out of order here because I want to make that land here. So consider this example here. I'll make it bigger in a second here. Okay, here is a big, complicated nonlinear function. It's one of the famous ones. It's not quite the symbol that you get when you boot MATLAB, but it's, you know, it's like one of those, right? It's called the 6 Hump Camel. It's a bunch of terms, which I can write down here. All right, so big, ugly, hairy equation. It has lots of local minima, right? You would expect this to not, it doesn't feel like it should be a convex optimization problem, right? That's when I show you those things and I say I'd like to find the minimum of that function, you should say you're going to have to do stochastic gradient descent, and you're going to maybe have to restart until you get the lowest one or something like that. This is low dimensional enough that you could sample and find it, but yes?
Is it true that it is always worth doing this technique before trying stochastic gradient descent? Is there a huge performance advantage?
Good. So the advantage of, if you can find a convex optimization, the advantage is that you can guarantee that any minima are global optima. That's slightly separate from which way you choose to go down to find the optima. You can actually use gradient descent to find the optima. Oftentimes in convex optimization problems, we have different solvers, interior point solvers and other things you might have heard of, that will get there faster. But when you get to really large scale problems, people are actually using gradient descent again to find the minima of even convex optimization problems. Okay, so those are slightly different things, yeah. One's the set of tools and one's the set of landscapes. Now, what's amazing is even if I want to find the bottom of the minimum of this landscape, if I search just in X and put it in through here, then that's not going to be a convex optimization. But if I translate it and I search in a different parameter space, which is this parameter space of P, I can make it convex and I can find the minimum. Right? It's crazy, right? So how do you do it? You say P of X, I want to say minimize over alpha. Okay? I'm just going to minimize alpha. P of X minus alpha is sums of squares. Minimize negative alpha, whatever. Okay, I'd like to find the biggest alpha, I guess. Let's maximize alpha if I put a minimize the negative of alpha. The biggest alpha such that P of X is definitely greater than 0. That should raise up until it hits the floor where this P of X is at the bottom, okay? And it turns out that's just a convex optimization. In fact, you can see it right here. I sampled a bunch of points. The minimum value I found was this, and sums of squares gave me that. Even better than my sampling, probably. Okay? Did I get the signs right? Yeah?
So how do you find a set of basis functions that makes it convex optimization?
Okay. So I think a good question is that's a good question, and I think another reason why polynomials are good. So let's see. Let me say it a slightly different way. Does this only work for polynomials? because that trick of writing it in a quadratic form should work for any phi, right? Any m, whatever. The reasons that polynomials are such a powerful class here is basically because we know what the basis function should be. That's one of the reasons, right? So one thing is that equation matching is linear constraints in the coefficients. That's a big one. And then we know the basis functions. We actually know a lot about that, and there's a lot under the hood. The simple way to think about it is if I have a polynomial x that has some degree d, then I can just list all of the monomials up to degree d divided by 2. Right, so if I have y to the 4th power, then I need somewhere up something that gets y squared in there because it's going to get squared. Okay, but I don't need y to the 56th power or anything like that. So I have a finite list of basis functions that I know is going to be sufficient. Okay, and actually it's smarter than that. People have done lots of deep thinking about there's something called the Newton Polytope, which is the simplest. That's even the starting point, which tells you which coefficients in your you actually have to keep, which basis functions you have to keep around. And people do a lot of things to try to make, to minimize this basis set or set to 0, anything they know has to be 0. And there's structure in polynomial equations that people, just since they study polynomials a lot, have figured out, okay? In fact, even I had a student that I co-supervised, Frank Permenter, that did a lot of good work in this area of trying to pre-process those basis functions in order to make these things work better. Yeah, the coefficient matching. And the other thing is that we roughly understand the gap. Let me. So we said that if you can find a sums of squares polynomial, it's definitely positive. It's not the case that every positive polynomial can be written as a sum of squares in this form. Okay, so there is a gap. If you're saying I'm searching over the sums of squares polynomials, you're not quite searching over every polynomial. But we understand a lot about the gap, and it's small. For the purposes of this class, it's not a big. Basically, there's not a gap, but we know there's a gap. Papers have been written about finding polynomials that prove that there's a gap, right? People write optimization problems and proofs to find a particular polynomial with rational coefficients, which is definitely positive, but is not a sums of squares. Okay, so the fact that you have to write a paper about that means they're hard to find. That's not quite a proof, but yeah.
Do any of the strategies for choosing basis functions help with the growth? Because doesn't m grow super exponentially the degree, or not degree and dimension?
The number of monomials will grow. It should be up to, it's up to degree divided by d divided by 2. But you're right, as you get multivariable polynomials, every permutation goes like that. Yes, every attempt in these algorithms to try to find the ones that must be 0 is an attempt to minimize that and keep the SDPs as small as possible. Yeah. Also, you would like to think that it's a convex optimization problem. If I have terms in here that just the solver should figure out as 0, then solving the STP should also find that sparsity pattern. But in practice, if you're asking, that is akin to asking for something to just barely be positive definite, right? If I had something that didn't matter here, and I had to set one of these terms to be 0, that's asking it to be right on the boundary of a positive definite cone, and that's the worst case for some of these solvers. So it makes a big difference, not just in the size, but also in the numerics, the ranks, and the... Okay, so there are some versions of this, just to mention it, that you can You can put constraints that guarantee a matrix is positive definite that are easier. You can put linear constraints on a matrix or second order cone constraints on a matrix that will guarantee positivity. So there are approximations of this that are linear programs or second order cone programs. If you need to really scale, there are ways to do that, but you give up something in the tightness, then the gap gets bigger. Yes?
What is the reasoning behind putting px minus alpha, the regularization term?
How do you find the minimum of a, so you have to put yourself in the mindset of, I suddenly have this new tool, there's an oracle that says I can search over the polynomials that are positive. Now I'm given a polynomial that is not necessarily positive. How do I find the minimum of that polynomial? I'm going to add in some extra coefficient, some extra term, alpha, and I'm going to push it until it lifts the whole thing up to being positive. And the smallest number that accomplishes that, or the biggest, my signs are, but the number that accomplishes that is the minimum value of the function. Right? It's actually the minimum value. It's the height. It's not the x value that made that happen. You can retrieve that. You have to go to the dual of the problem which I'm not covering. But if you know optimization theory, the dual of this of the solution will give you the x that causes that to happen. Okay. So yes, what you said, but just not just. It's like crazy cool. So what can we do with it? It happens to be very well aligned with the constraints we write for Lyapunov functions, right? Basically, the fact that we're trying to look over functions that are everywhere positive or everywhere negative is like magically well aligned with this sort of capability. So the natural question is, what can we do? How can we use that kind of constraint to start finding Lyapunov functions without sampling? All right, back to Lyapunov. Okay, another key observation here. If I have a dynamical system given by a differential equation that's polynomial, and I want to search over v of x that's polynomial, then v dot of x is also polynomial. It didn't have to happen, right? We could have broken out of our class, but this property is sort of maybe yet another reason why we like polynomials as an optimization. Okay, sines and cosines and stuff can work too, but it's really clean and good here. Now, there's an interesting question. I didn't actually, I didn't remember to put this in my handwritten notes, but there's another gap that's appearing here, actually, which is that you could have a f of x that is a polynomial dynamical system, which is stable. It's even stable in the sense of Lyapunov, but you can't prove that it's stable with a polynomial Lyapunov function v. So we're only searching over the polynomial Lyapunov functions, and we might not find one, even if the system's stable. Okay? But if I convinced you anything last time about the difference between cost to go functions, which are particular solutions to a particular partial differential equation, versus Lyapunov functions, which just have to satisfy this inequality constraint, the great thing about Lyapunov is that if you can find one Lyapunov function, you can find a lot of Lyapunov functions that prove stability. It's not this sort of narrow class. And these little gaps in practice, I think, just haven't slowed us down, right? if your system's stable, you can probably find a Lyapunov. But we do, again, know that there is a gap. Okay? All right, so let's give an example of global stability. Here's a polynomial dynamical system. It's a non-trivial one. If I were to plot the vector field, you'd see things spinning all over the place. I should have done that, but I forgot to, or I didn't. Okay, it turns out we know that there's a Lyapunov function that this function is a Lyapunov function for that system. We could try to certify that by algebra, but let's not. Let's ask the solver to just find a sums of squares decomposition. If it can find a feasible solution where this matrix is positive definite, then we're done. And it's like 2 lines. Maybe it's 3 lines because I have to import something, right? "15 lines with print statements," okay, but it's pretty small, right? All right, I'm going to make a new mathematical program, construct my indeterminants, which are different than decision variables, right? I write my f, write my v. Those are all worthwhile lines. That's pretty good, right? V dot is just the Jacobian of v times f. Add a sums of squares constraint, saying v dot, negative v dot should be a sums of squares. Solve. Okay? And then if I run that, it's just, it won't surprise you. This is a simple enough problem. It won't surprise you that it's instantaneous, but like all of the problem, it's loading Python is all of the work. Right? Successfully verified Lyapunov candidate. Okay? So, and there is an assert there, so it actually worked. Okay? All right. So what's cool though is, let's say I didn't know this. Let's say I wasn't given some clever Lyapunov function, because that was the annoying thing all the time, right? Was that sure you can prove Lyapunov if someone gives you this magical function, and 20 years ago that's what we were doing. We were trying to disappear for a long time, come up with a magical function, and you get a new system. Oh, now quadrotors work because we found a Lyapunov function for quadrotors. Okay, let's search for it. So instead, let's just say v of x is just a sums of squares polynomial. So I'm just going to write a bunch of terms, p mx, and search for p, because I'm allowed to do optimization, right? In my sums of squares framework, I can say minimize something or maximize something or search for some p that satisfies this. Okay, so I didn't have to know that those had coefficients. I'm going to make a function that has 1, x, x1, x2, all the combinations of that, and it should find the coefficients that satisfies that. And that's like 2 more lines to search for the global Lyapunov function. I'm going to say v is now a sums of squares polynomial in those variables. Oh, I add, just to make it well conditioned, I add a constraint, because there's too much freedom in this, right? It could find a v that's infinity, or it could find a v that's like basically flat. So just to make things good, I'm going to say that v0 equals 0, v1 equals 1. That's what those next 2 lines are. Sorry to be so mobile, Tobias. Right, so this is just saying add a linear constraint on v, that those things are 0 and 1, and then the rest is the same. Okay, I can run it, it doesn't assert, and it finds a v, okay? So that's pretty cool. We can now find Lyapunov functions. No sampling. Yes?
So the assumption that the dynamics is polynomial seems pretty strong, right? A lot of the systems we saw in class don't hold that. In practice, is there any value to taking a non-polynomial dynamics function and trying to approximate it with a polynomial to then use that, or do all guarantees just find out?
Awesome question. So the question was, we haven't, pendulums aren't polynomial. What do you know? And we haven't done polynomial stuff. So what good is it to have only polynomials? Yes, you can do Taylor approximations and do fairly well. You can even bound the error of your Taylor approximations. But rigid body dynamics, by the time we're done, I will hope to convince you that they are actually polynomial. You just have to change coordinates. So I will have a satisfying answer in a few minutes. Great question, though. In general, yeah, there are more general cases where you can do this, but polynomial is by far the most developed, and where the solvers are doing the coefficient matching for you, and we know how to write the Newton Polytopes, and we know how to do, so it really is, it's a practical constraint. And you can approximate lots of smooth functions with polynomials, right? The question is with what degree and how accurately. Good. Do people understand the basic idea? Yeah? Finding the Lyapunov functions, convex optimization, no sampling, guaranteed for all x, right? Better than anything we did with the Hamilton-Jacobi. Yeah?
What part of this guarantees that the unit is radially inbound?
Oh. So for instance, I actually, if you, did I do it in this one? I will typically write V is actually, I say that V of x is sums of squares, but I say V of x is a little bit greater than alpha or something like this, alpha times x squared. You can certainly put a constraint to say it's got to be bigger than 0. If P is strictly positive, then you should be good, right? As long as you know something about how when M vanishes. Right, but the most general way is you just ask it to always be greater than some very shallow quadratic function. Yeah? You have a different? Yeah?
Isn't it that it's not 0, it's always radially bounded?
Ah.
You cannot have a limit in a polynomial. So it's either 0 and it's flat, or it's radially bounded.
If it's positive, it's a positive,
Squares.
good, and it's got fixed degree, then it should always be radially inbounded.
0 out, even if you say V of 1 is 1.
Yeah, good.
I think.
I think that's probably true. The polynomials can't help themselves but blowing up to infinity, which is annoying, which is a source of numerical woes too, but good. Thank you, Tobia. Okay, now, just like we did, there's more to do, right? So, you have this now magic oracle. It says for all x, if I can find this, then for all x, P of x is greater than 0. But in practice, I don't care how good you are at control. If you put it on a humanoid and you claim that for all x, the robot will never fall down, that's just not possible, right? There's some x where no matter how good you are at control, you're going down, right? So I think global stability analysis is a sort of wonderful starting point, but it's not useful in practice, I would argue. Almost any reasonable system that we're trying to stabilize over some practical workspace, right? We'd like the robot, when it's in a reasonable initial condition, to have some proof that it's not going to fall down. Okay, but I've only given you a tool for all x. So if you have an oracle, you go to the Oracle of Delphi and you get to ask just one question, or you can ask a bunch of questions. It's convex, and you want to prove that something's good just over some domain D. Remember, Tobia gave you all the regional Lyapunov arguments. If you wanted to say for all x inside some D, then what question would you ask of the oracle? You can imagine if you're clever enough with the way you ask the question, maybe I can get an answer, right? Here's the trick, okay? Let's make sure we specify D with polynomials, right? That's what we're good at today, right? Let's say it's all the places where some polynomial function g is less than 0. Okay? That's the domain we care about. If I can say that p of x plus lambda of x, g of x, is sums of squares, where this is yet another polynomial, and lambda of x is sums of squares. I've got a transpose here somewhere. Then this is true. You could think of this is called the S procedure. It's called positive Nolenstads. It's called a few things. You can call it Lagrange multipliers for all I care. That's good. I asked Sasha Magretsky why it's called S procedure. What does S stand for? He's like, yeah, I'm pretty sure it's from. The idea was developed in Russia. But I don't think, but the Russian alphabet doesn't even have an S. So we don't actually know where it came, I don't know where it came from. And Sasha, I mean, I don't know if he was just messing with me, but I didn't get an answer that day from Sasha. But still, it's always called the S procedure. Let's make sure we understand it. So what's the idea here? So g of x, there's two cases, right? When g of x is less than 0, we're saying lambda is some polynomial that I've got with coefficients. I'm allowed to search for the coefficients, okay? I'm going to multiply something that's less than 0 by something that's always greater than 0, okay? So in the region D, G is only making it harder for me to accomplish this sums of squares, this positivity constraint, right? So certainly if I can still prove it, even though G is trying to fight my proof, right? Then certainly this has got to be true. Do you see that? If g is less than 0, then I'm pulling my function down in that region. If I can still prove it sums of squares despite that lead weight, then I've certainly got p must have been sums of squares in that region, must have been positive in that region. Okay, conversely, when g is greater than 0, p could have been negative, and this can contribute terms now that help me out and bring me back up. Okay? So in practice, this is a way, and if the degree of this polynomial goes to infinity, then you can actually get tight results about this. Again, we make a gap by having a fixed degree polynomial representing our multipliers. Okay, but this is the basic idea. So we can take our oracle, which tells us if a whole function is positive everywhere, and ask a question about it being for all x, no sampling, but over some set, defined again by the level set of a polynomial. All right, so how do we use that for, well, and just to give you the other, for completeness, if D was defined by an equality constraint, that's the other version of it, then I could prove that lambda is arbitrary. Because when g is 0 here, this can do nothing to help me. So p of x really has to be sums of squares on that place where g is 0. But away from 0, this term can help me out. So if I only have to prove that something's true over this manifold, then this is a sufficient condition for proving it. Not necessary, sufficient. Yeah? All right, so now you can imagine, yes?
Could you do Taylor approximation if your domain is not polynomial, and would it yield sufficient results?
We have done that often, and I've never felt bad about it. You can do it carefully, which is by, again, bounding the error of your Taylor approximation from the original one with constants or sector bounds or other things. But I would argue that a lot of our systems actually are polynomial. You can certainly come up with good examples that are not, but pendulums and acrobats and stuff, we're going to show you are polynomial. Interchange of variables, right? Okay. So let's put this to work in a region of attraction analysis with the Lyapunov functions. Regions of attraction using the S procedure. So for instance, just to give an example that we can think about with it, this will be a general algorithm, but just so I can draw pictures along with it. This was one of the systems that Tabia used. It's one of my favorite systems. It's the one that goes like this, right, with a fixed point at 0, and we know that the region of attraction is just between, so we know that you can prove stability of this with x squared, and we know that the ROA of the fixed point at the origin is the sublevel set where v of x is less than or equal to 1. If you want to certify that with sums of squares, this was, x dot equals negative x squared, then I can say, here's approach number 1. I can say that for all v of x less than or equal to 1, that implies that v dot of x is less than or equal to 0. That would be one way to write this. So this is my domain here. I can write that with the S procedure. I'll put the negative, I don't want to confuse you with the signs, but I'm going to put a negative at the end here, okay? What do I write? Here, I want something that's less than 0 when it's inside and greater than 0 when it's outside. So I'll do this. Nope. The opposite of that, right? V of x minus 1. Okay. I'd like this thing to be like this to be sums of squares. If I can find, so what are the decision variables in this problem? Okay. In order to write this out, I'm going to make a new set of decision variables, which are lambda. I'm going to say lambda is a new polynomial, which is effectively c0 plus c1x plus c2 x squared plus c3 x cubed. I think you actually need fourth order in this formulation. I'm just going to make some new polynomial with free coefficients. I don't know what c's are going to be to prove it. And then I'm going to say, find me some variable c subject to that constraint, negative v dot And I need this lambda x is sauce too, because that's the inequality version of it. So the only decision variables in the problem, as I've written it here, are the c's. If I can find some c's, then I've found basically a Lagrange multiplier that proves, that gives me a sufficient condition to know that my conditions are satisfied everywhere inside that set. Now there's a really key point. In this case, if we run it, we'll find that that it gives me one. It says yes, and I can prove that this sort of v is basically exactly 1. It's a 1 degree of freedom system, low degree, everything's good. So everything's tight here. But in general, all of these gaps that we've been building up, saying that there's not necessarily, not every positive polynomial is a sum of squares, not every polynomial dynamical system has a polynomial Lyapunov function, all these little gaps I've mentioned, we've been very careful to always have a proof going the other way. If you can find this, then everything holds going back, and we really do have a Lyapunov function. So it's not the case that I sort of flipped my logic on you somewhere. I'm confident that if I find this, I might not find it. It might be stable, and I can't find it. But if I do find it, I've got a proof. So I'm okay with floating point. All right, the hardcore people will go through and not consider it a proof until you have rational coefficients and everything like that. That's not me. Right, so up to floating point. If I find this, it's good. Does that make sense? Really? I mean, it's like you have to get your head around it. And we have hopefully a very good problem on the homework, because really the only way to do it is to bang on it, for me at least, to write some code and see how it works, okay? Now this was certifying, this was doing sort of a simple version of the problem, right? I wasn't searching for V, I was just certifying a known region of attraction. There are variants of it that can do more. I can search for V, I can do, there's a couple different ways I can search for the region of attraction. But they're nuanced. If I'm doing it if I'm doing a search for a global proof of stability, a global Lyapunov function, then I can just search for the coefficients of V. We already did it for the pendulum. We did that a couple times, okay? But once I do this, and I have to have my regional analysis, my Lagrange multiplier, if V has coefficients and lambda has coefficients, then I can't actually search for V and lambda at the same time. It's not convex in both V and lambda. Okay? There are versions of this. Again, you now have to think about, okay, I can ask this oracle anything. How do I reformulate my questions? And there are versions of this that you can write that look a little stranger, but that can get us a little farther. Okay? For instance, if I know V, I know the shape of V, but I want to search over different level sets of V. That's a simpler version than searching for all of V. So let's say I could make this a decision variable. We sometimes call it rho. In this formulation, it's still a non-convex, you get rho times the coefficients here, so you can't do that directly. But it's a scalar, so you could just set rho, check the sums of squares program, and then do a line search on rho, and actually very effectively just solve a handful of convex optimizations and find the biggest level set which passes these conditions. But if you're willing to go with me here, there's a slightly different way to write this that mostly I'm going to make you do on the homework, but I have enough time, I'm going to show it. Okay, approach number 2. We were talking on the way here. I was like, is the homework good enough that I don't have to do this on the board? Because a lot of times when I do this on the board, people are kind of like, you have to think about it for a minute. But let me try it, okay? Here's a similar set of conditions, which is also sufficient and happens to be better if you want to search for the level set at the same time, okay? I can say that if v dot of x equals 0, that implies that v of x is greater than or equal to rho, or x equals 0. Okay, if I look at all the places my function v dot hits 0, right? There's one place it's allowed to hit 0, that's when x equals 0. Everywhere else that it touches 0 had better be outside my region of attraction. Okay? I also have a constraint that I have to know that my v is convex at the origin. The Hessian is positive definite. So as long as v is going up at the origin, the first time it goes down, or it flattens out, every time it hits 0, had better be outside my region of attraction. Okay, you got to think about it, but that's a different way to also achieve a certificate inside rho. Okay, and it turns out that if you write that down, if you just use that in the S procedure, then the trick that happens is that now my rho is over here, my v dot is in here, and I can search for lambda and rho at the same time in one convex optimization. Okay? It looks like this. V minus rho, I have to pull out the origin. Again, we're going to make you think about this. The only way to really get it is to think it through. Minus lambda v dot, if that is sums of squares, then I can search for rho and lambda at the same time, and I have a proof of stability. Okay? And this also finds the Lyapunov function less than 1 is, okay? Now it gets very cool and very powerful fast, right? If I can do these things with domains, I can also do robust stability. Remember the robust stability argument we did with common Lyapunov functions, where we said I don't know what A is. It might be 10, it might be 11, but there's some range. You can imagine I can also have uncertain parameters, and I can put in more Lagrange multipliers. My program's getting bigger. I'm not going to pretend it's free, but you can start knocking out robust analysis via common Lyapunov functions searched with sums of squares. Okay? To try to make that land in the case of this cubic example, all right? So let's say I have now some uncertain gain. The way uncertainty enters in these things is, for nonlinear systems, there's different ways it enters, and they can do different things, okay? So here's my nominal system. You know that where the fixed points are and everything, okay? But now I've got an uncertain coefficient. So let me just draw a few realizations of that different curve with different values of delta. This is delta equals 0. Here's a few different versions of it, okay? So it can take all these different forms. What's the robust region of attraction for this? That, right? Wherever the worst case delta is on this side and the worst case on this side, I can still prove by finding a common Lyapunov function which works for all delta and for all x, for all delta in this interval and for all x in some sub-level set, I can find a common Lyapunov function that shows the robust region of attraction, even if you have uncertainty. Yeah? Additive uncertainty looks a little different. It's actually pretty cool that it's different in an important way, right? So what happens if I plot a few of these? The definition of fixed point is suddenly suspect, right? Where's the fixed point of this system? Well, if I talk about fixed point stability, if I'm asking for asymptotic convergence to 0, I will fail. Sums of squares is going to say no, right? But I can ask for invariance. I can ask for v to be less than or equal to 0. Especially, the real trick is to really get invariance. I ask at the boundaries, that I make sure that I don't go outside some boundary. Okay? And I can show that there's some set that is an invariant set. For instance, when you're a quadrotor, you're blowing in the wind, you cannot show that you will stay at the origin for arbitrary winds in some bounded domain, but you might be able to say that I never leave some region. And you see how that can be just another domain with more indeterminates. I have x as an indeterminate, and I have wind as an indeterminate. And wind is bounded by some amount. And for all x and for all wind, I can make arguments like this. Okay, here's an example that you're going to do on the homework, but I want you to see it in pictures on the big screen here because I want to make sure you understand. This is another, we find cool examples that are polynomial, right? That's the best case, okay? But this is a van der Pol oscillator. People hear of the van der Pol oscillator before? Just the name even, yeah. It's a set of polynomial equations up there, second order differential equation. It happens to oscillate, right? So if you start from any initial condition here, except 0 will stay at 0, other initial conditions will go out, and they come into this stable periodic orbit. When I start outside it, it comes in and it goes to that stable periodic orbit. And we're actually going to talk about how to prove stability of that when we get to the walking stuff. This is a good entry to walking. But today, we're going to use it as a trick. The cool thing is, think what happens if I play this backwards in time. So we're not going to think about the van der Pol oscillator. That's about periodic stability. I'm going to reverse time, which means I take all of those vectors and I basically, I negate them. Okay, it's not quite this making the arrows backwards, but it's inverting the stability. So what happens is the fixed point, which was unstable, becomes stable, and this line becomes unstable. All right, so that's sort of reasonable. What's cool is this becomes now one of those cases where you have so the region of attraction of the fixed point at the origin is the limit cycle from the forward time. So it's a non-trivial limit cycle. I can only get it numerically. In fact, I don't have a closed form solution for the path of that limit cycle. But we know the limit cycle. And the question is, can we find the region of attraction? Right? We get things like this, for instance. You will get things more elliptical than that, because we're looking only over second order in the problem set. Okay? You can look over find the biggest ellipse that fits inside this. This is a quartic. This is up to degree 4 polynomial. But I want to show this because, and you'll see it in your P set 2, everything we've done here is conservative. So when I'm done, what I have is an inner approximation of the region of attraction. There might be states that will get to the origin, which I did not successfully prove will get to the origin. But everything inside that region, I have confidence will get to the origin, up to floating point. Every decision has been made along the way to ensure that the conservativeness is in that direction. And I wanted to show, that I wanted to show the non-quadratic one because it's really not, just like the 6 Hump Camel, you're searching you're doing convex optimization in some parameter space. It does not mean that the region of attraction you're finding is convex. Just like we did an optimization of something that was a non-convex function, but we did it in a different coordinate system. Right? So the coefficients of the Lyapunov function, you're convex in those. But the level sets can be more interesting. So this is a case where we constructed a system, just picking some polynomials so that the known basin of attraction had this orange shape. We searched for quartic, I believe, Lyapunov functions on the inside, on this one, okay? And we got the yellow region. And the only point here is that the yellow region is not a convex set. It's just visually, obviously not a convex set. We are not restricting ourselves to searching over convex sets in X. It's a convex optimization, the parameters of V. It's a different thing. Okay, so you really can do these on, on quadrotors and everything like this. This is you're going to be able to write out a handful of sums of squares. You have to sort of do it once to understand it, but hopefully we give you a tool so you really can take, for instance, this was the LQR thing I showed you before, just running LQR on the quadrotor. And you can ask, what's the region of attraction of the linear controller on the nonlinear system? You can also ask, for instance, if you don't know what the mass is, and you get the slightly smaller thing, right? If you do an uncertain region of attraction, then it can prove less about the region. The region of attraction will only decrease if I add more constraints like that, okay? That becomes incredibly useful. In fact, we already needed it and didn't have it in one of our early examples when we did the energy swing up and balance controller, right? Remember how we pumped up energy, we stabilized the homoclinic orbit, but we didn't actually stabilize the fixed point. We had to actually switch into the LQR controller in order to stabilize the fixed point. When do you turn on the LQR controller? So I said 2 in the code that I wrote. I was like, 2, you know? So, but I did choose it as a sublevel set of S, and the reason is because now I can write the real code here, which is take the LQR controller, figure out its conservative estimate of its region of attraction, and once I'm inside that, then I can turn on the LQR controller and I'm good. And as long as I have a proof that my energy controller will eventually enter that region, I know I can turn it on, and I will eventually stabilize the goal. Okay, so how far do you go with this, right? So I think the math is clean and good, and I hope you got a sense for it here, but I really think you're going to have to do the problem set to appreciate it. There is a gap. There's this annoying thing that once you go to try to type these equations in, you will often say, your solver will come back saying, infeasible. Like people have, when sums of squares initially, when people started hearing about it, a lot of people tried it, and they were like, this doesn't work, right? And they kind of gave up on it. Because, and I was just maybe more persistent in my group, and a few other groups that have done it across the world, whatever, did a lot of work to figure out how to bang those polynomials into submission, right? It was like, find all the ways to zero things that really should be zero, right? Find all the ways to sparsify, make things smaller, get rid of all the numerical badness. It took like years and years of doing this, and now we're getting closer to having it be a technology. And so you should do this once, and hopefully you won't feel too much of that pain, but you just know what's going on behind it. But the way it should look soon, and for instance for your project or something, this is basically, what you should have as a tool now is you say, here's a system, it could be a quadrotor, it could be a pendulum, here's the fixed point I want to stabilize, ask, and what's the region of attraction, and it spits out V. Okay, and behind the scenes there, it's actually doing a bunch of stuff. It's like, for instance, it's taking V dot, it's looking at the Hessian, the local approximation. It's trying to find a change of coordinates so that both Hessians are numerically well balanced, right? It's like adding extra terms in front of the Lagrange. It's picking the degree of the Lagrange multiplier so that terms match as well as possible. It's doing a bunch of little things behind the scenes that you just don't want to think about that. Okay, so, but I really think it's to the point where you can think of this as a technology that, so this is using all the symbolic backend of Drake, so you can't do this in arbitrary simulators, but you can do this here, and you could use, find out what 2 is and put it in your favorite simulator, and you're good. Yeah. I've got like 3 minutes to convince you it's polynomial. Let me just, I'll do it quick. All right, rigid body dynamics are polynomial. It is a 3-minute thing. So, yeah, I don't get polynomial dynamics in general. right? I get these, even if in the zero case here, I got sines and cosines flying everywhere. So what do we do about that? Well, we're going to leverage this S procedure idea. There's something important about rigid body mechanics is that I do get sines and cosines going around, but I only get sine theta, cosine theta. I never get, for instance, sine L theta or anything like this. It only appears in simple forms. So let me just make a new variable. C is cosine theta. And I ask, so I can rewrite my dynamics in S and C. And the pendulum example I did before, which is in the notes and everything like this, does this behind the scenes. It uses S and C to write the dynamics and the derivative. And then it adds an extra constraint saying I only need to satisfy the Lyapunov conditions on the manifold where sine squared plus cosine squared equals 1. And in fact, basically all of rigid body dynamics you can play this trick. The one case is if you have a screwed joint. Don't do that. But I think other than that, every like standard joint configuration, prismatic, whatever ball joints, everything, you can always write them as a polynomial. Okay, so the tricks still work. Every time you do pay a price from adding these kind of things, but the solvers are getting better and better, the front ends are getting better and better. We can do things to like effectively erase these again in the back end, so you don't pay as much of a price.